Hi, and welcome to our fifth video and final video in our series on trade wind inversions. Today we're going to take a look at the lapse rate tendency equation, and in particular terms E and F, the two complicated terms related to clouds and diabatic heating that can influence the strength of the trade wind inversion. So if we go forward to our first slide here, recall that a couple of videos ago we introduced this lapse rate tendency equation here that has the change in the strength of the lapse rate associated with the trade wind inversion here on the left-hand side. And we introduced terms A through D and described their physical interpretation in our last video, focusing in particular on this divergence term, term D, that we had here for strengthening the inversion, while terms B and C move it around horizontally and vertically respectively. In this video, we're going to focus here on term E, which is our cloud scale vertical turbulent motion term, and then term F here, which includes a number of diabatic heating terms. Again, recall, just as before, we're evaluating this equation at inversion height, roughly 800 to 900 hectopascals. You can invoke this equation at any height that you want to, but for our particular purposes, we're focusing just at inversion height. All right, so let's take a look at term E here, our turbulent vertical mixing within clouds term. We have a second partial derivative with respect to pressure here, where pressure is our vertical coordinate. So we're looking at a change in some property within the vertical. And the second partial derivative tells us maxima and minima. It has the opposite sign. If it's a maximum, it is negative. If it's a minimum, it is positive. We're not going to need to get that complex here necessarily, but just keep that in mind in case you see terms like this in future applications. Here we have our turbulent vertical velocity, omega prime, and we have the cloud scale potential temperature here as theta prime. And so we've said that this term relates to turbulent vertical mixing within clouds, cloud scale motions more generally, but why ultimately are clouds important? What role do they play in influencing the strength of the trade wind inversion? And so just as we did with the divergence term in the previous video, we're going to take a look at this term physically first, not getting into this complicated math, but looking at it more from the underlying physics. What do the turbulent motions within the clouds do to the inversion? And then we'll take a step back and take a look at it analytically in terms of the mathematics that we have here through our second partial derivative term. So let's take a step forward. I have here a recent visible satellite image from GOES West, GOES 17, taken off of the coast of North America. We have Hawaii down here at lower left. And between California and Hawaii, we see that portions of the Pacific Ocean are covered by clouds. And these are different types of clouds. You have a number of open cell cumulus. We see cumulus just off the coast of California here and here. We have some more stratocumulus to even stratus clouds as you get a little bit further to the north, in this case in association with a large-scale cyclone. But during the summer months, noting that this image is from the late winter, early spring months, when we get to the summer months, you have the subtropical anticyclone dominating over the eastern Pacific, and so you get widespread stratocumulus to stratus clouds, typically here in the eastern part of the basin, and these become more of the trade wind cumulus types of clouds that you can kind of see down here south and east of Hawaii as you move toward that region. So if you've ever flown through a cloud, and I know many of you have flown at least once in your lives, you know that when you get to the clouds, sometimes it's pretty smooth, but other times it's pretty turbulent. There are turbulent vertical motions, both upward and downward within any given cloud. And so each one of these clouds doesn't just affect you as you fly through it in an aircraft, but it would affect a bird as it tries to fly through the cloud. And in particular, it has meteorological importance as well. That turbulence, the upward and the downward motion, transport air from the bottom of the cloud to the top of the cloud, top of the cloud to the bottom of the cloud. And it's horizontal as well, even as we don't perceive that nearly as readily as we do the vertical aspect of it. Motions that go into and out of the cloud in the horizontal as well. And as we'll see here in just a moment, that vertical turbulence, the mixing of air from beneath the cloud to above the cloud, has key importance for the strength of the trade wind inversion. So let's consider a generic cloud trapped beneath the trade wind inversion. So I've recreated our vertical profile of potential temperature here that you would expect to see in association with the trade wind inversion. An increase in height at an increase in potential temperature at all altitudes here, given by the orange curve, where potential temperatures are x-axis and pressure increases going downward here on our y-axis. But it's a relatively slow increase beneath a very sharp, very rapid increase associated with the trade wind inversion, and then a slower increase once again as you get above that altitude. So it's this level in here, near where I've drawn this cloud, where our trade wind inversion is found. And this original profile here in orange, we want to consider just what the turbulent motions within this cloud are going to do to affect that profile. And so we know that there are both turbulent upward vertical motions, where omega prime would be negative, and turbulent downward vertical motions, where omega prime would be positive within the cloud. And so if we consider that air lifted from the cloud base here from the bottom, note that it has a potential temperature value given by this spot here on the profile. If you take that air turbulently upward, it's going to have a lower potential temperature, this value versus this value, than the air that surrounds it. So omega prime is negative because we're dealing with a turbulent cloud scale vertical motion. But theta prime is also negative because that potential temperature that is being brought up by that turbulent vertical motion is lower than all of that of its surroundings, given the slope of the profile that we see here. So let's consider the other side of the cloud, where we can envision a downward turbulent vertical motion. So we know that omega prime in that case is positive for downward directed vertical velocity. But the potential temperature here at the top of the cloud is higher than all of the points below it. So that turbulent downward motion is going to bring higher values of potential temperature downward. So omega prime is positive, and theta prime is positive in this case here as well. So there's a direct correspondence between the two. Negative vertical velocity going upward with lower potential temperature, positive vertical velocity going downward with positive potential temperature perturbation here. And that key point, those signs are the same. They're either both positive or both negative. Recall that this term deals with the product of omega prime and theta prime. So if they're both the same sign, that product is always going to be positive for these vertical motions within the clouds that we have depicted here. So what does this mean? If we consider those turbulent upward motions here, it's trying to take this low value of potential temperature and bring it upward toward where it is relatively high. So it's going to try to take this upper part of the profile and shift it over to the left. So let's bring in the pen here and depict just what that would ultimately look like here. But for this turbulent vertical velocity going downward here, it's going to take these higher values of potential temperature that are at the top of the cloud and bring them down and increase the potential temperature here at the bottom of the cloud. So that's going to take the profile and cause it to shift to the right. Ultimately, shifting the profile to the right below and the left above is going to change the slope of that vertical profile. And in particular, it's going to make that slope less. So if we annotate this in, we get this green modified profile here, where we've shifted this lower part of the profile over to the right and this upper part of the profile over to the left. The slope of this green line here through the trade wind inversion is not nearly as steep as it was within the orange line that we had depicted before for our original profile. So ultimately, this results in the weakening of the trade wind inversion at the altitude at which it's found. Turbulent motions within clouds weaken the trade wind inversion. And in particular, this is the single largest contributor to weakening the trade wind inversion. So in our last video, we talked about how divergence related to variations in vertical motion on the large scale from one height to the next leads to the strengthening of the trade wind inversion, particularly close to the US West Coast. This term acts as the opposite. These turbulent motions associated with clouds trapped beneath the inversion act to weaken it. So there's a tug and war effect going on here. Divergence is trying to create a strong inversion. Subsidence aloft is trying to push that down closer to the surface, but these clouds that are trapped beneath the inversion are trying to weaken it and, as we'll show in some of the heating terms later on, trying to lift it to higher elevations. So keep in mind, this turbulent vertical motion within clouds term is the single largest contributor to weakening the trade wind inversion throughout the entirety of the domain between the west coast of California and the United States, as well as over to Hawaii. So if we want to take a look at this analytically here, we can apply a centered finite difference approximation to the second partial derivative. So we've seen this for the first partial derivative. It's the +1 point minus the -1 point divided by 2 times the distance between any given point there in the denominator. For the second partial derivative, here, given that we're looking at the vertical coordinate, we have the +1 point, which I've labeled as top here, plus the -1 point, which I've labeled as bottom here, minus 2 times the middle point. So let's say that I was evaluating this at 850 hectopascals. That first term might be that value at 800 hectopascals, plus the value at 900 hectopascals, minus 2 times the value at 850 hectopascals. And then the denominator is the difference in pressure between any two of those levels squared. So this denominator is always going to be positive because it's the square of a given number. We're not dealing with imaginary values here. So that numerator is going to control whether this is positive or negative. And so you're comparing the top and bottom added together to twice what's happening in the middle. And so if what's happening in the middle is larger than what's above and below, then this term's going to end up larger than the first part and you'll have negative. Whereas if what's happening in the middle is less than what's happening above and below, then the first part is going to dominate and the overall term is going to be positive. So let's think about this in our cloud example. We'll take top to be above the cloud, bottom to be below the cloud, and middle to ultimately be in the cloud. So let's think for a moment. What would we expect to see above the cloud? And what would we expect to see below the cloud if we're dealing with turbulent vertical motions within clouds? As you might think, those terms are going to be zero. Whereas here in the middle of the cloud, keep in mind, we said that omega prime and theta prime have the same sign. If you have upward vertical velocity, omega negative, you're bringing lower potential temperature upward, theta prime negative. If you have downward vertical velocity, omega prime positive, you're bringing higher potential temperature downward, theta prime positive. So no matter which type of the turbulent motions you're looking at, this product here is positive. Minus 2 times that is going to be negative. So 0 plus 0 minus a negative gives us a negative for this term, and thus the lapse rate tendency is negative, as we would expect physically from our previous slide. So again, turbulent vertical motions within clouds act to weaken the trade wind inversion. So that's all well and good, and that leaves us with one last term, or really in this case, set of terms for us to consider, our diabatic heating terms. And a couple of videos ago, we demonstrated that this complex negative partial derivative with pressure, with all of this stuff inside of the brackets, can boil down to some approximation, minus the vertical derivative of 5 different heating terms. One associated with convective precipitation, non-convective precipitation, evaporation, surface sensible heating, and radiation here. We said that those first 2 heating terms, which are related to precipitation, can be neglected because we don't often have precipitation within the trade wind inversion. We have clouds, but we typically do not see large-scale precipitation, nor do we typically see thunderstorms beneath the trade wind inversion, which makes sense. The inversion is a stable layer. We need deep upward motions to be able to sustain precipitation and thunderstorms, and we just don't have those in this case. So if we bring back Steve Harvey, so we get rid of those 2 terms here, and that leaves just those last 3 terms, evaporation, surface sensible heating, and radiation. So we want to take a step through each one of those here one by one to close out this lecture. So let's look at the evaporation term, and we're going to go back to our old friend, a cloud trapped beneath the trade wind inversion given here by the orange profile. So we know that we don't have clouds everywhere under the inversion. So there are regions that are cloud-free and regions that are cloudy. So specifically, that means that we have regions that are subsaturated where we don't have clouds, and regions that are saturated where we do have clouds. There are turbulent horizontal motions in the clouds, just as there are turbulent vertical motions. So we have turbulent vertical motions that detrain or export from the cloud. And we see that depicted by this black arrow here at right on the cloud. We also have turbulent horizontal motions that entrain or import from outside of the cloud. It's given by this arrow here on the left side. So the cloud, we view it as a coherent feature without necessarily thinking about the interaction of that cloud with all of the air that surrounds it. But the cloud is mixing, is interacting with the air above and below and to its sides, ultimately motions out of the cloud to the surroundings and from the surroundings into the cloud. And in both of these cases, you're taking air that is saturated within the cloud. We see the saturation in the form of the cloud, and you're taking it to where it is unsaturated or subsaturated in the case of detrainment. Or in the case of entrainment, you're bringing in subsaturated air into the cloud where it is saturated. So in both cases, we would expect to see evaporation. The saturated air that is going out of the cloud is going to become subsaturated, and thus there will be cooling associated with that. Whereas the air coming in from the cloud, from the environment into the cloud, is going to cause some of the saturated air in the cloud to cool evaporatively as well. So you're going to see a reduction in potential temperature associated with both entrainment and detrainment within the cloud. So that's going to try to take this profile and shift it to the left within the cloud layer that we have here. And so if we bring this forward and take a look at what that profile looks like, note how that modified profile is very similar to the original profile, except for this change here within the cloud layer itself. This only impacts within the cloud layer, and it shifts the profile to the left. So this has two effects. Here where the cloud is formed, note that the profile of potential temperature is now much more vertical, less of a slope, less of a change in potential temperature. So we've weakened the inversion right here in this narrow layer where the cloud was formed. But by virtue of shifting that whole profile to the left without changing it much further up, note how we have this steep slope that is now found at higher elevations above the cloud. So the evaporative heating term leads to the inversion weakening at the cloud layer, but strengthening it above. So in effect, you're pushing the inversion upward in association with this forcing term here. So let's now take a look at the surface sensible heating term. So we need to make clear the emphasis on surface sensible heating. The only contribution to this term comes from what is happening in the way of warming or cooling right at the surface. So we're considering air that passes over the ocean surface for this particular term. And so we have up here a sea surface temperature map here from mid-March of 2020 with the cooler waters pushing to the south and east along the west coast of North America. And then as you go from California west-southwest toward Hawaii, the water temperature steadily increases from about 13, 14, 15 Celsius off the coast of California to about 24 to 25 Celsius near to Hawaii. And so if we consider a generic air mass that passes over this entire region here on the southern and eastern periphery of the subtropical anticyclone that we would expect during summer, the air is going to be have a different temperature compared to the surface that differs between the west coast of North America and between Hawaii here. So stepping forward, we want to keep in mind that sensible heating always results in warming of that which is colder. So if the water is warmer than the air, sensible heating is going to try to warm the air. The water will heat the air from beneath. Whereas if the opposite is true, if the air is warmer than the water that lies beneath, the air will lose heat to the water, so the air will cool in that case. So if we think about California, a generic air mass of temperature maybe like 17 Celsius is going to pass over this relatively cool water of 12, 15, 16 Celsius. So in that case, the air is warmer than the cold water that lies beneath. And so the air will lose heat to try to make the underlying ocean warmer. And so you're going to cool the surface here near the west coast of North America because of the relatively cold waters that are found there. Whereas near Hawaii, where the water is relatively warm, the air that comes spiraling around the subtropical anticyclone here is going to start as being relatively cool compared to the warmer waters beneath at lower latitude. And so the waters beneath are going to warm the air that resides above. So it's going to increase the potential temperature of that near surface layer on that sounding. So let's take a look at what that means. Again, we return to our example here of a profile in the orange, and we've kept our cloud in here because we typically do see clouds beneath the inversion in these locations. So near California, as I mentioned, cooling near the surface reduces the potential temperature there. So in this case, it's going to take the profile and shift it further to the left. In that case, maybe let's use the green marker here to denote that that's going to shift over to the left. So if we add in that profile, we get something that looks like that with the green line that is drawn. It's very similar at the trade wind inversion and above, but note how that whole profile beneath the inversion has shifted over to the left. So now through the trade wind inversion, there's a greater increase in potential temperature over that particular layer. So consequently, we say that this results in a stronger trade wind inversion near the coast of California. That cold ocean current that comes down the west coast of North America helps to create a stronger trade wind inversion through this surface sensible heating term. Near to Hawaii, the opposite is true. We're going to take this profile here near the surface and shift it to the right because we're gaining heat from the underlying ocean. And so consequently, we're going to warm, and that leads to a profile that looks like this. So again, from the trade wind inversion on up, there's no real change in potential temperature, but beneath it, we've warmed. And so as you go through the trade wind inversion, there's not as large of a change in potential temperature as we saw in the original profile or as we see near the coast of California. So in this case, surface sensible heating leads to a weaker trade wind inversion. So there's geographic differences between the west coast of North America and Hawaii in this particular term's importance and forcing. So let's go to our last term, our radiation term, and we again need to go back to our example that we've used over and over through this video here of a cloud trapped beneath the trade wind inversion. So there's two types of radiation that we need to consider. We need to consider what's happening to shortwave radiation coming in and how the cloud is influencing that, as well as long-wave radiation that the Earth's surface is emitting toward outer space. What is the cloud doing in that regard? So let's move forward. So below the inversion, this cloud is blocking the incoming solar radiation from coming in. We see that on cloudy days here in Wisconsin throughout the year. You don't see the sun coming through, and so consequently, you don't get as warm near to the surface, especially during the daytime. However, this cloud also blocks outgoing long-wave radiation emitted from the surface from escaping all the way to outer space. A lot of that is absorbed by the cloud, and some portion of that is re-emitted back downward. So that's why nights are typically warmer when you have cloud cover as compared to times when it's relatively clear. So the net effect between the loss of incoming radiation and the gain of outgoing radiation favors that latter term. There's more that would otherwise be lost to space that is kept than what you're losing from coming in from the sun. So this would ultimately warm beneath the cloud, which would lead to the profile shifting to the right here. And so if we step forward and take a look at just what that actually looks like, well, got a little bit ahead of myself. Let's think about what's happening above the inversion in this case. So the same cloud, as we noted, is keeping the incoming solar radiation from coming through. In fact, it is reflecting some of that back to space, which is a net cooling effect. Whereas some of that outgoing long-wave radiation that came up from the surface and was absorbed within the cloud, some of it's directed downward, but some of it's also directed upward to outer space. And so this is a net cooling effect as well. So between these two, the outgoing long-wave radiation that is lost and the incoming solar radiation that is lost, we have a net cooling that takes place above the cloud. And so that's going to act to take this profile above the cloud and shift it to the left. Now you might recall that we've already considered a forcing term that had much the same effect, with shifting the profile to the right beneath the cloud and to the left above the cloud. That was term E, our turbulent vertical motion within clouds. And so together, this acts to weaken the trade wind inversion here. Radiation, the loss of incoming solar radiation, is overwhelmed by the gain in outgoing long-wave radiation, warming beneath the cloud, and the two processes above the cloud contribute to cooling there. So we get a weaker change, a smaller change in potential temperature across the cloud that is associated with a weakened trade wind inversion. So altogether, summarizing, in our previous video, we talked about four forcing terms. The differential potential temperature advection term we got rid of. Horizontal advection and vertical advection act to transport the trade wind inversion. The divergence term strengthens the inversion. The turbulent vertical mixing within clouds term, however, is the single largest contributor to weakening the trade wind inversion. The radiative heating terms each have different contributions. Evaporation weakens the inversion in the cloud layer, but strengthens it above. So we can view this as a term that's trying to lift the inversion, just as the vertical advection term, given that we're in the descending branch of the Hadley cell, is trying to cause the inversion to be found closer to the surface. So just as the divergence and cloud terms are kind of counteracting each other, the vertical advection and the evaporation terms are kind of counteracting each other in terms of the vertical structure of the inversion. Surface-sensible heating strengthens the inversion near California, but weakens it near to Hawaii. And this term can be kind of viewed similar to the horizontal advection term, where we said it didn't have much of an impact near California, but tried to strengthen it closer to Hawaii. So we have a geographic difference between those two sets of terms here as well. And then finally, our radiation term weakens the inversion, like we saw with the turbulent vertical mixing within clouds term. It weakens, it warms below the cloud and cools above the cloud, and so you don't get as steep of a change in potential temperature, a weaker lapse rate through that cloud. So altogether, that completes our discussion of the trade wind inversion and all of the forcing terms that contribute to its structure. In our next series of videos, we'll take a look at tropical jets and disturbances, focusing on the meteorology of Africa. So until then, thanks for tuning in.